Yeah, thank you so much. Yeah, maybe I repeat a bit. So we are talking about trace over matrices, and if we take trace of identity matrix, then it's dimensional of the Hilbert space. And if we take identity bounded operator over the Hilbert space, then of course this infinite dimensional. And in this case, we say that okay, this is not a trace class operator. So that's the notion. Not a trace plus operator. In other words, that's the topic of this section. We want to discuss what are trace class operators. Okay, so is this motivation is clear that why we need to really discuss trace class operator in a more systematic way for infinite dimensional Hilbert space? Is it clear to all of you? Okay. So now, so we try to follow more or less the same route, and then we will see which point we need to change. So from matrices, you also know that trace of two matrices, say A and B, this is same as trace of the other way around, B and A, where A, B are matrices D by D over K. In other words, if we have a general linear map, let's called S. So since we are in D, D, K, then trace of S inverse. So it's a general linear map, so inverse exists of a matrix M S is same as, because of tracial property, we can take this as other around. So it is same as trace of M for any matrix. Yeah. In fact, this is an identity. So what does this identity tells us? This tells us that trace is well defined. Trace is well defined on the space of linear maps is of linear maps of very important finite dimensional vector spaces. And in particular, this transformation shows us that this is independent of choice of basis. Also, independent of choice of basis. And that's a super useful property because then we can take whatever basis we like, we can compute trace, and we know that it's not a problem. Okay, so now we try to imitate similar structure, yeah, because if we have a finite dimensional Hilbert space, then everything, I mean, it's just linear algebra. So we consider orthonormal basis. Phi I, orthonormal basis. on K T. And remember, I think we discussed it, that the component of a operator. Uh, so, okay. So operator was usually denoted by T. So the component of an operator, say Ig, this is given by Phi T Phi J. Okay. And this is called the coefficient of the basis Phi I. And now this is expressed in terms of for the particular choice of basis. Okay. So now we write trace of T is given by, as you told, is sum. So Phi I T Phi J, sorry, is I because we need same. I equals to 1 D. Yeah. So this is a recap of linear algebra. And now the idea is S should be unitary then. No, it's not necessarily unitary. It's just general linear group is sufficient. So that is invertible, because by tracial relation we can bring this in front, and then this gives you identity. Okay. Thanks for your question. Okay, so that's the recap of linear algebra. Now we we want to use this structure to define trace class operator, because in general for linear algebra we have D, so that we know that there is no problem with uh, convergence. But usually I think now it's more or less clear, one of the main issue of infinite dimension is convergence, and that's part of functional analysis about. So now let us define. So as usual, H is a Hilbert space, and in particular it's a separable Hilbert space. Although, so today we will see how separable Hilbert space is useful in physics, but right now it's just a technical requirement. And we consider a operator. So later we will actually show that a operator to be trace classes must be a bounded operator. In fact, something more. It's a compact operator. But I don't want to take that route, because then I have to, I mean, anyway, we will introduce what is a compact operator, but very briefly. Okay, so now let T is a bounded operator on H, and this is called trace class if the trace norm, so this is called trace norm, trace norm. Okay. How it is defined? So let's try to imitate this thing. So we should, now you see, if it is a separable, then we know that we have countable orthonormal basis and how it is useful. So phi n t psi n, so it's kind of elements. Now this can be positive and negative, so we want to sum it up, and if it is negative then we don't know what's happening, so let's make everything positive. So we take absolute value. And now we sum up for, sorry, I am mixing indices. That's not a good idea. Let's use I as we are using before. 1 to D. I need a space. And now you will ask, okay, what is this phi and C? Yeah. So we say, okay, that it doesn't matter. I mean, it matters. So we take supremum over this. So supremum over phi and ci. So, okay, so let me read it again. So this is a bounded operator is trace class if a trace norm is finite, which means this is not infinity, where the supremum is taken over all integers supremum is taken over all integers d. Of course, okay, you can consider 0, but that's not interesting. And over any to finite list over any to finite list of orthonormal vectors. So phi1 dot phi d and psi1 dot psi d. And as you see, their length are same, of same length. Okay. So is this definition clear? So we basically try, we try to imitate this thing. So we imitate this, and now there is, I mean, we don't have a choice like, okay, which basis or which list of vectors we are considering. Then you say, okay, you consider all, so we take supremum over all orthonormal vector which has some finite length, and then we take supremum over it. Okay. And for finite dimension, you see that you don't need this supremum. You go back here, and then everything is nice anyway. All right. So one line definition: an operator is a test class if its trace norm is finite. So there is other way of also to define trace norm, but another day is equivalent. Okay. Now I have used this word trace norm, and I think we begin our lecture with something called norm. What is a norm? Norm vector space sort of thing. So first we have to show that this is actually indeed a norm. Yeah, how do we know this is a norm? And then I although I wrote it, but I didn't explain why I consider bounded operators. So yeah, maybe at this point I shouldn't. Let's think. Yeah, let's call it maybe unbounded at this point. We will see shortly that this is not the case. So first, let's check this is a norm. Okay. So check that this is indeed a norm. So what you do for norm, you put a scalar and you want to see what is behavior. In particular, it should gives you scalar multiplication. So trace norm, you put in the definition, and what will it gives? It will give you supremum over phi psi I. So I'm just copying from above. The only difference is that now we have a scalar C with the operator. Okay, and of course we can just bring it back by the property or axiom of inner product space, and this gives us C Fresnel. Okay, and then what else we need? We need triangular inequality. So let's also check that. So T plus S Fresnel supremum EI EI. Same expression as above. 1D EI T plus S EI. And again, we use the property from scalar products. So maybe not to make things messy, I use a different color. So this part is greater or equals to EI T CI plus EI S CI. Okay, and now you just use supremum over in front of all, and you will get trace norm over T and trace of S. So it's nice. Then this is called, this is a norm. So indeed, this is a norm. Okay, I also told that this has to be a bounded operator. Why is that? So let's see. Observe. So now we consider a unit vector on Hilbert space, which is not kernel of the operator. Okay, so okay, let U be a unit vector such that U is not equals to 0. Then we can set V 1 by TU norm, and so kind of normalization. Yeah. Okay. And now we apply the definition above with D equals to 1. Then we see that T U equals to T U V. Sorry, it will be the other way around. Oh no, TU, yeah. And this is small, is bounded by definitely Fresnel. So this shows what? Remember, there is this operator norm. That operator norm is bounded by Fresnel. So if something is trace class, then operator norm must be finite. And if operator norm is finite, then T must be bounded operator. Okay. Yeah, so that's why initially I was giving this, but now you see that. So we can actually restrict our interest from the beginning to bounded operator. That will also work. But I think for the first time, it's good if you see the link why something is like this. Okay, so are there any questions so far? Okay, well, there is no question. Now, let me denote the set of trace class operators by I1 on H. So this is set of trace class operators. Now, if T is a trace class operator and S is a bounded operator on a Hilbert space, then TS, or the other way around, ST is actually a trace class operator. Okay, so in a way, trace class operator are nice. So with bounded operator, there is still trace class operator. All right. Now I give you as a theorem. This is something called trace functionals. Theorem trace functional. So now I believe all of you are familiar what is a functional. These are distributions, right? And if you have started looking at your homework, then I hope you have seen there is a problem about distributions also. So whether you have done it or not, I hope things are familiar to you. And just to recall what a distributional do, it takes some function and splits up some number. Okay, so as before, we have a separable Hilbert space H. And if this is a separable complex Hilbert space, maybe, right? So separable complex Hilbert space. Okay, so if this is, then there exists a linear functional, then there exists a linear functional called trace from, of course, from trace class operators. And since this is a functional, definitely this will map to, since it's a complex Hilbert space, that's why I wrote it, C numbers. Satisfying three properties. So the first property is this trace functional. So if we take an element of trace class operator, then trace will give a number. The number can be positive, negative, and it's a complex number. So we take its modulus, and this is bounded by the trace norm. Next property is this trace of this operator is trace of unitary t. Now U is a unitary operator. And third property is the usual for cyclicity property of trace. Trace of Ts equals to trace of St. So now let's put quantifier for all Ts. Okay, no, we don't need all Ts. So T is the usual trace plus operator. Okay, I mean nothing usual as element of trace plus operator, trace of T, and then for all S bounded operator and U. Um, okay, bounded unitary operator are also bounded, but unitary. Good. And now we have one more, which is where we actually motivated with. What was our initial motivation from linear algebra? This guy. So we have a generalization of this guy. Number 4, trace of T is given by a goes to 1 to Phi T Phi. So Phi are orthonormal basis. And before it was the dimension, and now what is the dimension? This is infinite. Okay. So I give you a bit time. Yeah. So that's the generalization of what you know trace from linear algebra. Well, that's a generalization. There are other traces as well. But we will only discuss trace over Hilbert space. Okay. So you can give trace by the similar expression or analogous expression for linear algebra, but it's only for trace class operator, not for any bounded operators. And then you have the other usual property that you know for trace class operators. So are there any questions? Comments? Okay, I do not see anything. Now, as I try to emphasize, and you will start to see from today why, in the context of quantum mechanics, self-adjoint operator are something super important. So we have already shown that trace class operator are bounded. We also talked about positive operator. So these three can be actually glue up and gives an interesting result. So let's see. what it gives. So I wrote as proposition. So as usual, H is a complex Hilbert space. And let's consider T a bounded operator on H. So if T is self-adjoint and positive, we have discussed positive operator, right? So positive operator is positive, which is gives positive for any element of H as a uh, acting on the element and then taking the scalar product. Okay, so if T has further two property, this is self-adjoint and positive, and Ci is an orthonormal basis, then the trace of T, sorry, the trace norm of T is given by the expression probably all of you have anticipated, T I equals to 1 to infinity. Okay, that means if we have a self-adjoint and the extra two properties, then you can just compute using the usual definition of trace. In other words, if this is a positive operator, then the trace norm and trace are same. Okay, and that's why you have this expression. Yeah, sorry again, I am skipping almost all the proofs because of time constraint. But yeah, so that's an important property that is very useful in doing concrete computation. So are there any questions regarding this proposition? Okay, so I don't see, but anytime feel free to have your questions. Or if you feel lost, send me a text, unmute yourself, whatever is convenient for you. Now let's try to connect with, again, probably the very basic structure of trace we start with. That is, some of you told, this is sum of diagonal element. So can we have something for trace class operator? Yeah. And there is something, it is known as Lidlsky theorem. So theorem Lidis yes, I don't know how to pronounce it, but okay. So as usual, we have H. Now this is important that this is separable Hilbert space. And let T be a self-adjoint bounded operator on H. So Dudisky tells that T is trace class if and only if T is compact. I haven't told you what is a compact operator that I'm going to tell you now, but let me finish this section first. Compact and its eigenvalues, let's give a lambda I, satisfy, eigenvalues satisfies lambda I. This is a self-adjoint operator, so this can be positive or negative, but real. So we want to sum it up. So again, take modulus, sum it up from I to infinity. And that is precisely the trace norm. And I mean, it's a trace class, so trace norm is finite. Okay. And now more restrictive, which is that, in other words, we can say that, okay, let me write it. If T is indeed trace class, so now, I mean, by this, I mean that we are not assuming this is bounded self-adjoint, just trace class from the beginning. Then trace of T is precisely kind of the matrix generalization of the matrix expression, you know, sum of. So what is the was that sum of diagonal, and that's what is given by eigenvalues. And this sum converges. Okay, so now all are infinite. So whenever we have convergence, we have to say converges in which sense? So converges absolutely. Which is, I think, quite evident from this expression, right? So that's what absolute convergence. Isn't trace bounded by trace norm? Yes, it is. If the operator is positive, then they are equal. Otherwise, yes, you are right. Okay, so now I have to tell you what is a compact operator. I mean, as I told, there is other approach where one first defines compact operator, because these operators are also very important and it arises in many places. But I tried to be minimalistic, I hope, which is more or less evident to all of you. So I try to introduce as less as possible notation or concepts. But that also missed something. So there is a very beautiful spectral theory for compact operators. So we are missing that. Okay. But okay, you have to accept, or we have to accept some missing. So let's go. What is just as briefly? What is a compact operator? So write a different color. No, T is a compact operator. So by a compact operator, so now it's a general, I mean, okay, anyway, so it's a compact operator. We mean that, so yeah, maybe I use now L, not to confuse with this T. So an operator L is compact if, so L is a bounded operator on Hilbert space. That means it maps element from Hilbert space to Hilbert spaces. Okay, good. So now to be a compact operator, if L maps bounded sequences of H, I mean, of course, everything is on H. Maybe I write this way so that is clear. Okay, so this is a bounded sequence. So you apply it. And now, if the image of this bounded sequence has a convergent subsequence, okay, is this definition clear? Mm. You can also say bounded operators are those which maps bounded subsets. Sorry, compact operators are those which map bounded set, because you take a bounded sequence which is more or less that corresponds to bounded set, and we have a convergent subsequence. What is a convergent subsequence? That's a compact. Why it is compact? In the relative sense. So two relative compact sets or subsets. So this is a generalization of usual compactness notion. So I mean, what you expect for a compact operator if you think naively? So this is an operator on bounded, so of course it will take some bounded sequence. Okay, now in general, an operator maps a bounded sequence may not be I mean, since it's a bounded operator, it will be a bounded sequence. But to be a compact operator, you need something more restrictive, and that must be a relatively compact subset. Why relatively? Because we are in the relative setting of relative topology. And so, I mean, you can say that if a operator maps a bounded set to a compact set or relative compact set, then this is a compact operator. Yeah. So in a way, you define this operator in terms of its image. So you see that you start with boundedness, but you go with compactness, and that's called a compact operator. Okay. As I told, this is very important. It arises many places. It's a beautiful property, but yeah, like many things, I'm not going to. I don't have time to go detail of any of this. So if you are not comfortable, you can just forget about these blue things. Uh, so maybe that's really interesting part of Ladisky theorem, that even in infinite dimensional setting, you have a generalization or analog of the definition you know from linear algebra. All right. So, are there any questions about traceless operators? So, have a look. In the meantime, let me ask, is it okay if I take tomorrow an hour extra with 15 minutes gap to compensate yesterday's lecture? Maybe I make a poll. Okay, and then please, I mean, we have only 10, so you can write. What about rest of 8 or 7? Okay, let's 6 more. So what about others? Do you have problem if I take an hour extra tomorrow with a 15 minutes break? Okay, I'm not sure if rest of participants are on a screen. So thank you, all of you, 3 of you who said yes. Then tomorrow we will have an hour extra lecture to compensate yesterday's lecture. Yeah, before I go to next topic, are there any questions? In physics, yes. There are situations when compactness is used. For instance, when we do spectral theory, when we want to show, I mean, not always, but most of the time, that unbounded operator has a discrete eigenvalue, then what you usually do, you remember we have this resolvent. Resolvent is an operator. There is a theorem which tells that if resolvent is compact, then it has discrete eigenvalues. Yeah, in physics terms or intuitively you can think this way. So think about unbounded operator, okay? So unbounded operator, you have no control. You give up something and it may send you somewhere you have no idea about. Bounded operator are much better because you know that it will be somewhere in the Hilbert space. Okay, and now you want to ask more in the sense that, so compactness is a notion you can think something like that, not escaping to infinity. Yeah, this is a naive idea, not exactly. So if something cannot escape to infinity, loosely speaking, it's a compact thing. So compact operator are those to which if you fit something, they will not split up something at infinity. Yeah, like a very vague way. uh, I think we will see some concrete example. Yeah, and basically right now we are going to start quantum mechanics. So now we will see more concrete. It may not be today, but at some point we will see. Okay, thank you for your question. Okay, so if there is no further question, then let me change a bit the theme. So far we have been into in the realm of pure maths. So we were trying to understand how operators on infinite dimensional Hilbert space behaves, how to describe them. We study some of their properties, and some we learn some of the notions. And as I was telling you constantly, that this is essential to understand something called quantum mechanics. And historically, this is how this is introduced and developed. Although now this is an independent subject and used in many other places, but our emphasis is on quantum mechanics. So let me give you not even an introduction, say a glimpse of quantum mechanics. Okay, and next, more or less all next lectures we will doing some aspects of quantum mechanics, and now, yeah, you will see how these things arise. So um, yeah, let me write anyway an introduction. Oops. Yeah, I should not really say an introduction, but I don't know what is even brief. Maybe a brief introduction or something like that. But never mind. So I know this is a diverse audience. So let me start with a big idea. In case, so there are some mathematicians also who might not be familiar with this thing, and of course there are some physicists, some engineers, and all. So the idea of theoretical physics is something like that. So we have a reality. Maybe I put it like a nature. Okay. And things are happening in nature, right? For instance, we are doing this lecture course, someone is swimming, someone is sleeping, and lots of things happening. Okay. And all this part of the nature. And from ancient time, people wanted to understand nature. Okay. So to understand what it means actually, or how do we really understand something? So that's actually a very complicated question. And to best of my knowledge, is not, there is no say, complete way to describe what is really meaning by understand something. There are philosophical issues. Um, and I'm not definitely going to go through this discussion. But the time we are living, our view is that, okay, we observe that most of the thing in the nature has something common. And one thing is universality, right? If you observe something, there are people from various places. I think there are 7 different time zone people are attending this lecture. So if you do some experiment in any of your place, and if you do the same experiment with the same situation in other place, it will give you same result. So that's called the universality or objectivity. In a way, one of the uh, fundamental tenet of physics is that it is objective, very objective. It doesn't depend on who you are, how you view. Yeah, it should be very objective. All right. And we see the phenomena in nature, and we want to describe it, and we want to understand, not only to describe, we also want to understand why something is happening. So not only why or what, but also why. Okay. So by a theory building, loosely speaking, we have a mathematical description of nature. Okay. But this is very idealized. Okay. So so okay, so this is idealized. By idealized, I mean that in mathematics, you define things which may or may not exist in nature. And in fact, most of the mathematical quantity doesn't exist in nature in a very strict sense. For instance, if you think about a point, yeah. So what is point in mathematical sense is probably nowhere in nature. But there are situations when you can approximate very well things in nature as a point. Okay, in that sense, this is this idealization or very well approximated. So this is always an approximation of this guy. And this bridge, what is we are up to? Loosely speaking, let me call theory. Okay. So theory is the bridge or the way uh, we map a natural phenomenon to a mathematical description. Not always math. I mean, it doesn't need to be mathematical at priori, but it turns out that mathematics is incredibly useful and effective to describe nature. It might have something else, but it didn't happen. And why it didn't happen, there are some interesting papers and people think this is not very clear. I mean, why it is, but that is the situation. So that's why by description, I mean mathematical description. But in general, a theory building might have something different also, but that has not been happened. Now, how do we understand a theory is correct? Again, there are different criteria, and one of the criteria I think everyone agrees is that when you make this bridge, so this one side of this bridge is this idealized description that we build up based on our intuition, our knowledge, and everything. And the other side, we have the nature, who doesn't care about what we do or not, right? Nature doesn't care about our axioms, our understanding, or anything. But we have to care about nature. So this is where we have experiment. Okay. So our idealization has to be a very good approximation of this experiment. In other words, we visualize, idealized, philosophized something, and if it can explain the experimental result, then we say, that is a right theory. Remember, or note, it is not always possible to check each and everything of the theory. It may, but it not always it's possible. Sometimes it is possible, but for fundamental theories, it may not ever be possible. So how do we say a theory is correct, okay, or right, or truth? So then we have to actually specify what do you mean by that. So there are different sort of truths. For instance, there are mathematical truth, like all the theorems are truth. These are mathematical truth. Yes. So by a mathematical truth, we mean that you have a set of axioms and a set of rules, and if you can derive something without making a mistake, that's mathematical truth. That's all. But there is something called physical truth or empirical truth that is here. And theoretical physics differs from mathematics, or I mean, it not. I will not say drastically, but one of the difference or fundamental difference is that theoretical physics, the truth is empirical truth. That's the most important thing. Okay. So we want to describe this thing. We want to describe right experimental output. And if we can do that, then we say our theory is correct. Otherwise, we say our theory is not correct. But again, in this context, correct mean that based on the empirical evidence. It may be a truth in a mathematical sense. Okay? So a theory can be mathematically correct, but physically incorrect. That's possible. And the other way around is also possible, that a theory is physically correct, but it has mathematical problems. However, part of physicist, mathematician, what you want to tell, thinks that no, this should not happen, or this is not the way. So they thinks every right physical theory has to do with something mathematical truth. In other words, they think that all physical theory can be described in correct mathematics. Okay, and that's, I mean, not everyone will agree, but I would say at least that exists. It's called something called mathematical physics. So if I write this way, our whole arena is theoretical physics. Okay, so and then there is a tiny part where people think we do not only think about physical reality and physical truth, but we also care about mathematical truth, mathematical rigor, mathematical understanding. So they are demanding more. And I must admit, they are currently the tiny community. Yeah? So mathematical physics is a subset of theoretical physics. Some people will say, no, this is a subset of maths. Of course, this is a subset of maths. But whether this is a subset of mathematical theoretical physics depends. You can also consider this is a interaction between theoretical physics and pure mathematics. So um, yeah, maths. Yeah, you can also think, right? So those who have already attended or have some knowledge about quantum mechanics, so there are different theories, and we will think something about called quantum mechanics. Why it is called that, we will discuss a bit. Uh, you might not see any of this or some of this. The reason is most theoretical physicists think this mathematical proper way of understanding is not necessary, or this is kept for mathematicians. So they are not bothered by this. Again, it's a democratic, I would say, world partly. So anyone can have their opinion. And I do respect them. Okay, if you like, it's up to you to decide. On the other hand, there is a small, tiny group of people who thinks no. Since we have a right physical theory, there must be a proper mathematics to describe it, because mathematics has been so influential, so successful so far. Why it should not successful here? Yeah, so they don't, and that's usually what is called mathematical physics. Sometimes people also call mathematical physics which are not rigor. Uh, yeah, depending on community. Sometimes the people also use this word physical mathematics. Yeah. But again, I'm not up to tagging, just to give you a big picture where it sits. So this lecture was actually designed from the mathematical physics philosophy. That's why I wanted to discuss this. In other words, we do not want to only understand nature, but we do want to understand their underlying mathematics properly. So we want both. We want both, best of both. What we want, best of nature. We want best of maths, and then we want to have an understanding. And that's why we have so many abstract things in a very condensed way. But now you will start to see how they are. I mean, you have seen some example, but now you will see more concretely. Okay. So, are there any questions about the philosophy, or the strategy we are going to follow? Or if you have any comments? Okay, so apparently, thanks for your comment. Okay, thanks also for your comments. Apparently, we do not see any question. So, okay, let me give some references first, because anyway, I shall be also very um fast or brief. So, if you really want to study references, so there are many references, of course, yes. And what I am going to write is not any way the best references or the compulsory references or the most important, not anything. It's just some of the standard references I'm going to write, and I'm going to follow. You are absolutely free to read whatever you like, but just read anything standard. So first book I would like to recommend is Walter Moretti. This is called Fractal Theory and Quantum Mechanics. So this is published by Springer. I think the current one is the second edition. Next one I would like to recommend is, just a minute, I have to like the name of the book. Yeah, Gerald Tisval. This is called Mathematical Methods in Quantum Mechanics. Let me just write QM. This is by American Mathematical Society. Another book I would like to recommend is by Arno Boom. This is also called Quantum Mechanics and by Springer. This also has several editions. I think now is the third edition. Another quite standard book, I would say, is by Jujon Sakurai. And now I think the latest one with Jim Napolitano. This is called Modern Quantum Mechanics. So depending on which edition, it depends on different publisher. I have the old one, only by Sakurai. One book I like personally, but it's a bit different flavor, is by Claude Kuhutanoji. So this is a huge book actually. It's a two-volume book. Uh, but of course, I mean, definitely, you don't need to read everything. Uh, Bernard Thieu. I don't know how should it pronounce because they're French. And then Frank Levy. Again, sorry for my pronunciation. So this is also called Quantum Mechanics and by Willivich. And last is, I would say, I mean, not last, but least, is an absolute classic by Paul Dirac. It's called The Principles of Quantum Mechanics, Oxford University Press. It also has several editions. I have fourth edition. And of course, there are many interesting books. Also modern books where you can get more about this quantum informatics and this sort of thing. And all these books are nice. So I just wanted to give, like, who have no idea, at least to see. So this is kind of uh, from maths to physics order. So depending on your taste. This one is very mathematical. I would say the canonical choice if you want to understand quantum mechanics from mathematical viewpoint or mathematical quantum mechanics. Cell is also very mathematical. Both are very renowned mathematical physicists. Cell is actually a mathematician. Moretti is a very prominent mathematical physicist. Arno Bohm is a mixture between maths and physics. Sakurai, one of the standard book from physics viewpoint. Kyohutanoji Dyulebu is a French book. If you are familiar with their style, as I told, it's a thick book. It's a different style, but a very standard, very good book. And Dirac, one of the, I would not say founder, but the founder of systematic quantum mechanics. Yeah, it was actually Dirac quantum. So Dirac's PhD thesis is actually first systematic development of quantum mechanics, and the book is more or less a updated version of that. And that is very thin book, not very thin, but thin book, but it's an absolute classic. You can get lots of insight why something is like that, okay, which is not available in later books because people don't need to talk about those anymore. And yeah, as I told, again, there are many more interesting books, so you can read whatever you like. There is no bias. But I just wanted to give some idea in case anyone is completely new. Okay, so now before going to discuss what is quantum mechanics or what we are going to discuss, yeah, maybe a few words about quantum mechanics. So let's again, especially who are from non-physics background, we are in this arena. And if you are 126 years before, if you go back, then there was Newton's classical mechanics in a very general form by Lagrange, Hamilton, Maxwell's electromagnetism theory, and fundamentally that's all. And people was looking at nature, and apparently everything was explained by this theory, except if you look at the Mercury, this uh, solar astronomical observation, you see there are some deviation after decimal values. Okay, point. But what really shakes is the so-called black body radiation. So, what is this? If you are not completely familiar with this at all, just think about a hot body, yeah, like a cup of tea or something. And then what you see, it radiates. So you have a thermal radiation. And a physicist want to understand how the radiation varies, what's the nature of the radiation. And as I told, back then we have these theories, and people try to use those theory to explain this. And if you use this theory, one of the prediction is that with frequency you will have this radiation curve diverges. This something called Rayleigh-Jeans divergence. If you are not familiar, just take as a word. But the main thing is that the theory existed before 1926, uh, predicted something was not matching with the experiment of black body radiation. Okay. So since it was not matched, people were thinking, oh, what's the problem? And then, of course, if something doesn't match, people try in various different way, and different way people are doing. Um, Apparently, around 19th century, a German physicist, Max Planck, he was a professor in Berlin. He was also thinking about this problem, and then he wrote some expression uh, based on this experimental result and some heuristic idea and some intuition, and that expression matches with the experiment. However, you cannot derive that expression purely from the fundamental theory existed then, because it has some feature that was really kind of contradictory. I mean, not kind of, some in some cases contradictory with the theory existed then. Okay. However, as I told, he didn't have a systematic derivation or a very systematic way to understand this. And then apparently there was some other thing like the spectrum of hydrogen atom and sort of thing. Again, if you're not familiar, take as a story, because we are not going to hydrogen atom, but we will at least solve one problem, and then we will really see how theory and experiment, what was the issue. But just I want to give you a big picture of what we are heading to. Okay. Um so the punchline is that existing theory cannot explain certain experiment. Okay, and then there is a kind of by hand theory that could explain experiment, but then people ask this question: why the theory is like that? And people start working all over, and a very young postdoc back then, Werner Heisenberg, he was a postdoc of Max Born in Göttingen. He wrote some different multiplication that was not known from the theory back then. And apparently, he realized if one uses the different multiplication, then one can actually explain the experiment in a systematic way. And that's the beginning of a new era, the so-called quantum mechanics. Why it is called quantum, we will see concretely, but now just take. So Heisenberg didn't realize the multiplication here using is actually matrix multiplication. It was Max Born, his host professor in Göttingen, who realized that Heisenberg is doing what is matrix mechanics. But apparently it was very counterintuitive. Why there is matrix in nature and this non-commutativity and all these things. So from conceptual viewpoint, what Heisenberg was doing is very different from existing thing. And those things are now what we call classical theory, and what Heisenberg or initially started with Planck and many other people is called quantum. Why again? I shall explain why it is called quantum and why it is called classical. So that now that take this word like it's a new theory, new development. Um, and then apparently after 1 year or two, another he is not so young, uh, quite I think he was around 40. Erwin Schrödinger, he also derived some equation, and from that he actually said that okay, what is this experimental outcome is actually eigenvalues of some operator. And now I think all of you know what is eigenvalue. Mhm. And this viewpoint was also very different. I mean, before people was not familiar with experiment with eigenvalues and all these things. But now then is the issue that okay, there is this guy Heisenberg, a young guy, and then relatively non-young guy Schrödinger. They can both explain theory, but they have a different theory. And then after 1 year, actually, Schrödinger showed there is a link. Uh, so they are doing actually the same thing. So one theory is called Heisenberg formalism or Heisenberg picture. Still, we use this word. Another is called Schrödinger picture, of course, honoring them. And as I told, Schrödinger proved that both are equivalent. And then again, I told like this was systematic, but yet not from first principle. Very young guy at the age of only 24. Some of you are might be at that age. He wrote a PhD thesis in Cambridge, and his PhD thesis was called quantum mechanics. So he saw Heisenberg's work, he saw Schrödinger work, and he realized how one can systematically go in this picture. And he actually developed first systematic description of quantum mechanics. And there is also a picture named after him. It's called Dirac picture. And the book I suggested you, this is actually a updated version of his PhD thesis. You can actually find Dirac PhD thesis online. If you search, you can find it. It's not a big thesis, but you can see at the age of 24, someone literally gave the systematic framework of quantum mechanics. Not everything was correct in Dirac's work, but just think about this thing. So if I write naively, so some names, Heisenberg, picture, Schrödinger, picture, Dirac. Okay, and then with time, other people came and they also developed other picture. One of the prominent one is actually initially due to Dirac, but it was made popular by one of the most known physicists, probably Richard Feynman. Okay, and that's called the path integral formulation. Okay, and then so on. Yeah, it's keep going. So roughly speaking, this is called matrix mechanics because the multiplication Heisenberg used is actually matrix multiplication, and Heisenberg didn't know it. This is called wave mechanics because the name Schrödinger equation that you have already seen, in some sense, reflects the wave, not in a literal sense, but in some sense. So Dirac give the systematic development. This is called, so Dirac has many contribution. One is this bracket notation or bracket quantum mechanics. So maybe I just write bracket for simplicity. And also he initiated it, but he didn't develop later, but it was Feynman who developed more this path integral approach. And then so on. Now, a guy, I think I have told you several times his name, and there is no other way to skip his name, is John von Neumann. So he was also a young postdoc in Göttingen, but he was a postdoc of David Hilbert. Remember, Heisenberg was a postdoc of Max Born. He was a postdoc of David Hilbert. And he was also aware of this development happening in physics, and he was also interested. But none of these things are mathematical rigor, and he was not happy. So path integral came a bit later, but these things. And he was not happy about it. So he thought, okay, maybe he took this work to make this picture. So we do not want to only understand nature, but we want to understand in such a way that everything is mathematically correct and rigor. Okay. So he was arguably, as far as my knowledge, the first person who took to make quantum mechanics mathematically rigor. And he also developed quantum mechanics. So yeah, he has various contributions. One thing is the so-called density matrix approach. Also this operator approach. Yeah. So loosely speaking, von Neumann wanted to rigor this matrix mechanics. Okay. So matrix are not actually the appropriate thing, and that's the reason why we need to learn something more than linear algebra. So had matrix is the right thing, linear algebra is nice. I will not make your life hell with all this technicality and lots of things. Yeah, abstract nonsense. What you want to say? So this is was von Neumann who understood that that's not the right. It's just is it a good starting point? It's a pragmatic approach, but that's not the right thing. All right, and then other people, of course, contributed this thing. And there are other approaches of quantum mechanics. These are not all. Okay, there are other approaches of quantum mechanics. So if you continue in von Neumann's footstep, then you get something like algebraic approach. Okay, so this is the algebraic approach or algebraic quantum mechanics. If you continue Dirac and then Feynman, path integral, this is this constructive approach. If you want to continue this in a more mathematical way, you will probably go the geometric formulation. Okay. Dirac has many achievement and contribution. One is that I will tell you, and maybe you know that how you get the transition from classical to quantum, and that later gave rise to so-called deformation approach. So deformation, quantization. And as I told, there are many more. So all this approach has their pros and cons. So some can explain something better, some can explain something less. Um, but something this approach, so deformation approach is also related to algebraic approach. Yeah, you can consider this as a subset of algebraic approach or algebraic. So there is not one algebraic approach, there are several. And this produced something remarkable that neither geometric nor constructive approach has able to produce, and that is existence of quantization. Also, I haven't told you what is quantization, but there is something called quantization, and you can then ask whether this quantization exists or not. And using deformation quantization, uh, there is this famous work by Kontsevich who proved that kind of quantum mechanics exists. And this is so remarkable result in mathematics that it was awarded Fields Medal. So you see, to understand, to explain something physical, it's not the first time, there are several times, but this is one of the instant. This is a physics-driven problem that results in a Fields Medal in pure mathematics. All right, and yeah, and then there is algebraic approach, which is very active in these days. Deformation quantization is also active. Constructive quantum field theory is not that active, I would say. Geometric approach is also active, but yeah, I don't know how active, but probably not as much as the other. But maybe constructive is more less list. So in this lecture course, we will mostly follow this, try to understand matrix mechanics or the operator algebraic way. Maybe I also write here, operator algebra, or it's also known as von Neumann algebra. So we will not go much in this algebraic approach. We will keep confined with operators, and that's why I try to give you this brief about operators, what is called what is not called what. If you are interested and time permits, then we can definitely talk about this algebra, but we will mostly confined with operator theoretic viewpoint. In other words, we want to understand quantum mechanics from operator theoretic viewpoint. And you will see that there is a reason why I want to do it, because this gives you one of the most cleanest viewpoint that usually, for instance, path integral approach cannot do. But path integral can do some other thing which is not possible. As I told, it's not a complete winner. Okay, so there is a reason, and the reason is mostly that there is a clarity. You can get something unique, but you also lose something which path integral can give. Yeah. So there's the very, very vague and broad viewpoint what I want to do in next maybe 5-6 lectures. So before I start, are there any questions, comments, or your wish, like you want to learn this thing or want to discuss something? Yes, what you want to ask? You can unmute yourself and have your comment, what you wanted to.
So, sir, I'm wondering how to following this path from the foundation of quantum mechanics, then to nowadays apply quantum mechanics in our. Sir, can you hear me?
Yeah, I can hear you. Go on.
Okay. So then we end up with something like quantum field theory and string theory. So how can I follow this path in uh, in in a fundamental or as known path or map to be yeah what I want to say it's I wanted to I want to don't miss anything in the path of quantum field theory or strength. So I believe if I master very well quantum mechanics, I will be and the classical fields, I will be strong enough in quantum field theory and or any advanced topics, I think.
Yes. Okay. So the rough picture is that. So we have quantum mechanics that we are going to discuss very, very, very briefly. And then there are several problems in quantum mechanics. Um, and in fact, one of the big problems is quantum foundation. So quantum foundation is not still settled, not from physics viewpoint, neither from maths viewpoint. Okay. So to try to solve some of the problems or inconsistency in quantum mechanics. So quantum mechanics usually, as you will see, in the non-relativistic setting, and people wanted to add relativity by mean special relativity, and then it turns out that this is not consistent. So what people did, they add something extra, and then they formulated what is called quantum theory of fields or quantum field theory. And currently, this is the best quantum theory we have. Best means, again, in terms of experiment. So computation from quantum field theory matches with experiment like maybe after 8 digit of your decimal point or something. Yeah, so it's really amazing. Okay. Then people wanted to add gravity. So-called Einstein relativity or general relativity. And this gives rise to so-called semi-classical gravity. This is also called quantum field theory on curved spacetime. Okay, and now the holy grail, according to some people, you want to quantize whatever that is, and that something should give you quantum gravity or theory of everything. This is probably the most stupid wording, theory of everything, but in popular science you will find the word a lot. But yeah, I just wanted to write. Okay, and now we do not have a quantum gravity theory yet, but we have certain models like superstring theory. Loop quantum gravity. Just me write QG. Causal set approach. Causal fermion approach. And maybe people also discovered something more. I mean, I do not know. Okay, so yeah, so kind of this a very very big picture or very non-detailed way as your work. So you want to go here, and then the first step is of course to understand quantum mechanics. So yeah, if you understand it good, you are doing one of the say basic requirement of superstring theory. However, of course, as you see, and it needs there is something word called super, so there is supersymmetry on that also thing. I do not know this, so I am not a competent person for superstring theory at all. In fact, not for any of this. But yeah, this is a there are many things to go. You can ask people who are expert in this area what to do, but I can at least assure you that we are kind of the first stage. Anywhere you want to go, you need this. And this is not only to understand nature. Nowadays, lots of engineering is happening in nanoscale. And if you want to understand and devise thing at nanoscale, you also need knowledge of quantum mechanics, even for certain engineering problem. Also, now it's a very fashionable thing nowadays. Quantum communication, quantum computers. This has lots of potential, and some of words are just too exaggerate. Uh, but okay, definitely they have potential. So if you want to also go in this that area, again you need a good foundation or at least good understanding of quantum mechanics. So unless you do completely classical theory, anywhere you go, a good knowledge of quantum mechanics is going to be helpful for any of your endeavor. And if you apply abroad and you want to take some standardized test like GRE or something, then quantum mechanics is also part of those tests. So if you learn it good, you can also do good in those tests. So does it answer your question? Okay, there is another comment. So a very beautiful work by Feynman is that we can directly use Feynman rule without performing path integral every time. Yes, that's true. There is this Feynman diagram, and that's really make quantum field theory closer to people. Um, so I read this story somewhere. I couldn't recall where. So there was a conference where one of the famous quantum field theorists of all time, Julian Schwinger, gave a talk, and professors from other universities they attended. And then when asking, okay, so what is he talked about? And they took lots of notes and they said, okay, we have to sit and then understand what he was talking about. Because Schwinger is known, so one of the best computation was once done by Schwinger, this electron gyromagnetic ratio. Okay. And so Schwinger is always very precise and very, very systematic and complicated. And then people were asking, but wasn't Feynman there? Because Feynman was always the guy who kind of like a magician who say, "Oh, you don't have to think about lots of computational complexity. You just do this in a very intuitive." So he was the guy of intuition, I would say. So yes, Feynman path integral, Feynman diagram has this beautiful way. In a way, you can visualize particle scattering in some sense. That's true, but it has also limitations. So you cannot always do Feynman path integral or Feynman diagram. But for most of the cases, yes, you are right. So in quantum gravity, it is very difficult to imagine what would happen when gravity and quantum effect become strong. Yes, it is, and no one knows. No one knows, and probably some of you are going to solve it. I shall be more than happy to hear that. There is a new field where we combining entanglement effect with particle physics. What is this new field? Could you please let us know more, or maybe you can unmute yourself and tell us?
So in particle physics, we usually take particles and calculate the transition rates or transition matrices. And if we first consider the possible spin state, like using the Clef-Gordon coefficients, we are bounded by this Clef-Gordon coefficients that which spin states are allowed to transit into which states, right? So the entanglement effect is very similar. That if you know that the two particles, for example, the electron and positron, will make the spin singlet, it will make zero. So if you know that one particle, one electron have the spin up, the other wherever in the universe, it will have the spin down. So we are now considering this quantum entanglement, where there is an entanglement in the spin structure, and then calculating the rates. And the rates, the decay rates, are usually considered as the physical observable. But before detecting the rate for a particular system, the idea is that it can decay um, to more particles, and there is the superposition. There is a probability of getting into different final state particles. But as we are only now detecting the one possible
I think you became mute.
where we have the superposition of um, many different
You became muted again.
Can you hear me now?
Yes, I can hear you. I don't know about others, but as far as my side, there was a muted period. What about others? Do have others also can listen to her? Okay, so then probably it's my side there was problem, but yeah.
No, sir. I think she have weak internet connection, I think.
Okay. So by yes, you mean that you are also having same problem. Okay, sorry, I misunderstood.
Yeah.
Is my voice clear now?
Yeah, now it's clear. Keep going.
So I was saying that in particle physics, we used to calculate the transition matrix. And if we take the initial state particles and consider the specific spin configurations, those spin can be entangled with each other. For example, if you take the spin singlet of electron and positron, and we know that one electron have the spin up, we know the positron would have the spin down, so that they can make the spin singlet. So I don't know the exact idea, but the idea is that whether or calculating the decay rate, which is the physical thing, we are going one step back in where there is a superposition of many possibilities of different spin of different final state particles with different spin configurations. So that's a kind of new field where we are combining the quantum information theory and quantum field theory together.
That sounds very interesting. I mean, entanglement is really an interesting phenomena. Unfortunately, we do not have time. But if time permits, I definitely want to touch a bit about entanglement. And this is one thing where algebraic approach gives, at least to best of my knowledge, the best and the cleanest description of why we have entanglement and why entanglement is not like that sort of thing. And yeah, if we can relate with particle physics, then it will be really cool. So I really thanks for sharing your knowledge and experience. I really look forward to that. So anyone else who want to share his view, opinion, comments?